Okay, this is part 2 of our same standard, PS2.1. So if you remember, PS2.1 is looking at a relationship between magnetism and electricity. We've already looked at part 1, and we're just sort of going to review over part 1 because part 2 is the complete opposite. And we need to remember what part 1 is so that we know how it is a complete opposite. So I'm going to go back here, and we're going to look at this picture. And this animation. This animation, you can see that you have this thing moving, okay? And it is moving not because someone is making it like you see down here in the corner. Electricity is already provided. So what happens when we connect the electrical current, okay, when we connect the battery, we get a magnetic field to be produced around that wire, and therefore it causes it to turn. So this is what we call an electromagnet. I want you to highlight. You can use whatever color highlighting you want to. You don't have to be specific to the color blue right now. And with an electromagnet, the relationship that we have is that we create a magnetic field. Okay, that's really important to remember because the opposite's going to hold true with part 2. We're going to create a magnetic field, but we're going to use an electrical current. Okay, so you're going to see that part 2 is the complete opposite. So let's go ahead and look at the other part of this, and that is what we're going to call electromagnetic induction. So we still have the word electromagnet in there, but now we're going to talk about the induction aspect of it. So I'm going to come up here. We're still looking at go ahead and highlight the standard at the top of your paper because this is what part 2 is going to look at. We're still looking at the relationship between magnetism and electricity, but this time we're going to focus on generators. We're going to generate electricity. Okay, so you've probably heard of a generator. You may have a generator at your house. If you've ever been to fishing along some of the area rivers, they may say that they have a certain time that they're generating, and that just means that they are producing electricity with water that is flowing through the dam. So the water level is going to be higher than usual, and it's also going to move faster than usual. So we'll talk more about that in a separate lesson. But we're going to look at generators. And we're going to look at the factors that increase or diminish the electric current and the magnetic field strength. We've done this pretty much with an electromagnet, but remember, we're not looking at an electromagnet. We're looking at a generator. We're looking at the idea of induction. So let's go ahead and fill in the blanks here with part 2. You should have highlighted. I'm expecting to see some highlights on your paper in Cami, so make sure that you are highlighting there. Part 2, this is what we're officially looking at, and I just highlighted that up there, but here we go. It says, with electromagnetic induction, over here you can see that when this person is turning this crank, and this crank is attached to a coil of wire, what it does to the light bulb. When that person is turning it, the light bulb is glowing, but when the person stops, the light bulb doesn't. So what we can basically look at here and observe is that with electromagnetic induction, which this animation in part 2 is showing us, we can induce. Induction simply means these words. I want you to write down all of these words because they can all mean the same thing. They're all synonyms. So if you hear the word induce, it also means to produce or to create, to make, to generate, or to cause. So just keep that in mind. There are lots and lots of different ways that it could be written on a quiz or on a test, and I want you to be familiar with what induce means, okay? So with electromagnetic induction, we can induce an electrical current using a magnet and a coil of wire. So look, we don't have an electrical current here. We don't have a source of electricity. We are causing an electrical current to be formed by moving that wire in the presence of a magnetic field. So we are generating electricity. Okay. In part 1, we had an electrical current. We had an electrical energy source. And that caused a magnetic field to be produced. So that's how they're opposites. And this is sometimes confusing for students. So just sit back and think about it for a second. Go back and look at your videos as your intro videos from electromagnetic induction and compare it to electromagnets in general and just sort of see what's going on with all that. Okay. So a couple of things we need to know, and of course you should already know what electrical current is. We've been talking about it, but since we're producing it this time, we're going to be very specific in what it is. And it is a flow of electrons that are moving through a wire. So I want you to write that down in a text box in Cami there. So it's a flow of electrons moving through a wire. And then when those electrons are moving through a wire, basically we're going to end up with the magnetic field that is produced in this particular instance. A galvanometer, there are 3 different examples, and there are thousands of different examples. You can have digital ones, you can have analog ones. There are lots of different varieties of a galvanometer, and it's a generic term, okay? And I say generic because a galvanometer is simply a tool used to measure the flow of electrical current in a wire. There are different types, but they basically do the same thing. They measure electrical current in a wire, but they're called different things. So I want you to write these down for the 2 bullet points that you have in your notes. The first one is the definition to a galvanometer, and then the second one is the idea that it is a different type. And those different types are given the name of voltmeters, ammeters, and there's a wide variety of other things as well. Those are not the only types, okay? So just be familiar with that. Anything that is recording electrical current is something that we would want to use to see if that movement takes place. So here you can see a V, that means volts, okay? Over here, this has a big A for amps, and I'm sure you've heard of amps. You probably haven't heard of an ammeter, but you've probably heard of amps, okay? And that's just how much electrical energy that a speaker, and probably what you're thinking, would put out. This is an electronic form, a digital form, or actually just an electronic form of one, while these are more of your analog. Okay, so I just want to sort of show you a different variety. Some of them will actually read out a digital number on it. Once again, these are analog, just looking differently from one another. So let's look at how to induce or make an electrical current. You will be doing a lab, and you will do similar things. So here we go back to the same picture here of how is this individual able to turn a crank and allow this light bulb to light up. And it has to do with the fact that there's a coil of wire, and that wire is going to be a conductor, a copper form of wire, and there's also a magnet there. Those are the 2 things that we have to have, okay, as far as a structural component. We have to have movement. If you don't have movement, as you can see, the light bulb won't light up, okay? So there's a couple of ways to get that movement, okay? And that's why I've shown you these 2 pictures. Over here, we are moving a coil of wire, okay? But over here, we are moving a magnet. So here we're moving a coil of wire around above this magnet. Over here, we're moving a magnet through a coil of wire. And if we were in the classroom, you would be able to look at this lab and be able to do this. It's a little bit difficult to see just because you need a lot of wire to do this, a lot of coils, I should say, of wire to do this. But look what happens. If you look at this, this is your little galvanometer. I want you to write a G right here because this is your galvanometer in each one of these instances. This is recording electrical current, okay? So this is your electrical current that is being picked up. And in this very first one, when it says that the magnet is moving in, you get your galvanometer to move in the same direction. So yes, I want you to draw the arrows. That's important to remember. When you're moving the magnet here to the right, your galvanometer moves to the right. Here, there is no movement. The magnet is sitting within the coil of wire. It doesn't matter that it's sitting within it. It has to move. And because it just was sort of left, nobody is causing it to move. There's nothing to move it. Notice your galvanometer. It's at 0. This represents 0. There is 0 electrical current. Okay? Now, when you pull it out, okay, so they picked that magnet up out of the coil. They have pulled it in this direction. Yes, draw your arrows. They have pulled it into the left. Notice what your galvanometer did. It moved to the left as well. And so now it says, hey, we have electrical current that is flowing from right to left. Okay, that is the importance, number one, of seeing, do I have electrical current being produced, is using this galvanometer, but which direction is the flow of electrical current? Okay, and we can see here that there is no electrical current when there is no movement. So what you are putting in that box is this: the magnet or coil of wire must be moving in order for electrical current to be made. And there may not be a box, but you're filling in that information right below what it has to have. So when I talk about movement, keep in mind that it doesn't just have to be a magnet moving back and forth inside of a coil. It could be the coil itself being moved around this magnetic field that is produced, okay? That magnetic field, while there is movement going through that copper coil of wire, allows electrical current to be able to flow into this light bulb. So that's really, really, really important to keep in mind, okay? Now, how can we change the amount of electrical current? We looked at different ways that we could change the amount of magnetic field that was produced, depending on the size of the batteries, depending on how many coils we had. There were a couple other variables, and variables just means things that we can change to make it more or less. The same thing happens when we look at these pictures. So we're going to look at picture A right here first, okay? This is the same picture you have on your paper and your notes. It says an electrical current is induced, produced, generated, created, whichever word you feel more comfortable with. You just have to be familiar with all of them. When you move a magnet through a coil of wire, because the magnetic field is changing relative to the coil of wire, meaning it's moving with the magnetic field. So what we see here is this: the galvanometer moved, okay? You can see where those little red lines are not just in a straight up direction showing zero. Zero on a galvanometer is basically going in an upright position. If it's to the right, if it's to the left, that means it is producing electrical current. So what this is saying is that if we have movement, that means that we're going to have current, electrical current. And if we don't have movement, we don't have electrical current being produced, okay? So this particular picture is actually going to show movement, and it's going to show movement because there is electrical current being produced right there. That's what that red line shows us, okay? And that person is moving this particular magnet. In letter B, okay, what you're going to fill in the blanks with over there is this. If you look at this picture, it says a greater electrical current is induced if you move the magnet faster through the coil. So if you look at this hand, that sort of indentation of where the hand was compared to where it is right now, they're moving it faster than it was over here in picture A. So when you have faster movement, there's going to be more electrical current being made. And if you look at where those red lines are, you can see that those red lines went further to the right than it did over here. And that's just simply saying, hey, we have more electrical current being identified by this galvanometer, okay? Letter C. When we look at picture C down here, what we can see here, it says a greater electrical current is induced if you add more loops of wire. So if you compare picture A to picture C, you can see that there is a coil of wire in A, but in picture C, those coils are a lot more and a lot closer together. So it says this magnet is moving at the same speed as the magnet in B. So it's moving pretty fast, and it has more coils. So once again, you can see that hand, it's moving as quickly as it is in B, but it's producing more magnetic field. If you look at this, it went further here. It went all the way to the edge compared to where it went in B. Okay, it didn't go all the way to the edge because there are more coils. Same amount of movement in B and C, but more coils in B and C. Once again, the coils are the same in A and B. The coils are the same in C and D. The number of them are. And then finally in picture D, it says the induced current reverses direction if the magnet is pulled out rather than pushed in. So it's just like that picture that we looked at above on the previous slide. If you reverse the direction of movement, that reverses the electrical current. It's sort of like when you flip the battery on some of those virtual activities. When that battery reversed, so did the flow of electrons. Well, when the movement reverses, so does the flow of electrons, and the electrical current is going to move in the opposite direction. And the reason that I know that, I see that movement in the opposite direction. It's moving to the left now, okay, instead of to the right. So that's what we're looking at as far as how we can change the amount of electrical current that can be produced. It's very similar to the idea of how we can change the amount of magnetic field produced by changing different variables. This has to do with coils. This has to do with movement. And you could actually also change the size of the magnet, and that would also change it. None of these pictures identify the magnet difference, though. Okay. So to introduce the last final sort of what do we need to know about part two before we do our lab is just what is an electrical generator. And some of you may have this at your house, and when the lights go off, the electrical generator picks up and you still have lights. But you are using gasoline probably to generate that electricity. It's probably a gas generator. So what is the definition? That's what I want you to write down next to the word electrical generator. This is the definition of it. It is a device, okay, just like the electromagnet was a device. It's an actual structure that transfers mechanical energy, moving machine energy. Moving energy could be due to any of these sources that you see on this picture here, whether it's due to the wind, whether it's due to the water, whether it's due to steam, whatever it could be your hand moving it. You are considered a machine, okay? But it's going to take moving energy that could be in the form of a machine or a moving object, such as wind blowing through a turbine, wind or water going through the material in a dam that we'll look at more specifically in our next lesson. And that movement through those materials, when there is a magnet involved, when there is a coil of wire, is producing electrical energy. This is a very, very simple electric generator. Here is your device to record electrical current. Remember, that's a galvanometer, voltmeter, ammeter, lots of different things this could be called. Here is your crank. This is going to be a human-involved movement. Here is your coil of wire, and here is your magnet. And when we turn this crank, that turning of that crank will turn that coil of wire within that magnet, and that light bulb will light up, just like we saw in that animation prior to. So when we look at how a generator works, there's a couple of things here that you need to fill in the blank with and make sure that you have that completed. It says, if you move an electric wire inside a magnetic field, you make electricity flow through the wire. In effect, you generate electricity. That's why we call it a generator. Okay. Another word, though, is induction. It's how we can induce an electrical current. So here we have that basically idea that we have it connected to a material. Instead of a battery here, that's not really that would be me moving it. Okay. So that's not accurate over there as far as there being a battery. That would be me moving the material, not a battery supplying energy to it. And this is that idea right down here. Here's that crank. Instead of there being a battery, there would be you moving it. Okay. These are horseshoes type magnets and that coil of wire in there, and it would light this light bulb up. So let's look at this next slide. And this next slide is a gentleman who actually is why we have the microwave oven. Okay, he invented it. So he's going to explain to us sort of how a generator works. He's going to talk about AC/DC current, not the band AC/DC, but AC current, alternating current, and DC current, which is called direct current. I don't really need you to know the difference between the two, okay? But if you're interested in that, and because some of you may be, you can look at page 157 for more information in the book that I gave you. Okay, so let's go ahead and look at this video.
This is a generator, and it consists of a rotor that has wires on it connected to metal bands, which are called the commutator. And in order to make electricity, one must move a wire next to a magnet. And here are the magnets. Put those on there and turn the crank, and now the light goes on. And you notice that the green light is on, but the red light is not on. You turn the other way, this is connected as a DC generator now, and depending on which way I rotate, I get plus or minus. If I want AC, I move over the contacts so that we have what we call slip rings. Okay, now you notice that both the red and the green light simultaneously because it's AC. So one can have both AC or DC depending on how one makes connections to the wires that are being rotated through the magnet. But if you take the magnet away and rotate all you want, nothing happens. You've got to have a magnet and the wires. And that's how you make electricity. And you can do it by any means that allows you to turn that shaft. You can have a windmill, you can have a water wheel, you can have a turbine which has got steam that blows against a bunch of vanes. That's all there is about electricity. You move a wire next to a magnet. Except you have to make them big to make it useful for anybody.
Okay, and as you can see, they made it really big, and that's why you have a generating power plant, and why those coils, those yellow things that you saw in that video, were huge, 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 huge coils. So you have to have a lot of mechanical energy or a lot of movement to be able to move those huge coils, and that's why you're going to use water. You're going to use wind, not necessarily right there to generate electricity, but we'll look at that in another time. So in your next lesson, what you will be doing next time is looking at a virtual lab where you will try to sort of investigate and see how you can generate electricity.